It's the same deal with b. Watch what happens when I alter this. You can see that this changes the scale of things. If you want to talk about it this way, it moves the hyperbola further away from the origin, but no matter how far you go away, you're still going to have, you can see it right there, you're still going to have these points of intersection. They'll just be at different locations, right? So the feature of the sketch that indicates that there are two square roots is that there are always two points of intersection between these two equations here. So when you're solving simultaneously, you'll always find two solutions. That means there will always be two square roots to any complex number. So then it says, part B, investigate how the sketch changes when either A or B or both are negative or zero. So let's take those one at a time. Let's have a look at the negative case first. So let's bring these back into something a bit closer to what we started with. All right, let's see what happens when we change A to be negative. Right now it's 1.4. Watch what happens as I shift it over to a negative value. Oopsie daisy. It's quite cool to watch. Here's me making a smaller and smaller. You can see those two points there on the bottom, we call them the vertices of the hyperbola, the bits that are bent in the middle. They're kind of getting closer and closer together, right? As I get closer to zero, they actually collide. We'll come back to this case later. And then, whoa, what just happened? Let's go back to the positive. This is what the hyperbola looked like before. You can see it has like a left and a right hand half. But then when I cross over, A becomes negative, you don't have a left and a right half to your hyperbola. You now have a top and a bottom. And what I'm going to do is I'm just going to let this animate and you can see it changing, which is quite satisfying to watch. So when A is negative, the key question is what happens to our solution with the red graph, our points of intersection, I should say. Well, you still always get the 2 points of intersection. You can see there, it's highlighted by Desmos with those gray circles. Don't look at the intercepts, look at the points of intersection with the red graph. No matter where your green graph goes, even when you've got a negative value, you still have that pair of solutions. Let me hit pause on that guy there. Let's bring that now to the middle. Let's have a look at 0. So what happens when A equals 0? Well, A, if you recall, A is the real component of the complex number that we started with, A plus IB. So what this is saying is, what if you don't have a real component? What if you have a purely imaginary number? Well, what that tells us is, when you have a look at these solutions, the real and imaginary part of your two solutions there, you can see they're equal in magnitude, right? So this makes sense because if you've got complex numbers that are equal in magnitude like this, when you multiply them together, the argument to say 1.285 plus 1.285i, the argument to that will be pi on 4. You can see I'm counting it, I'm measuring up from the positive real axis, so pi on 4. When you multiply that number by itself, the pi on 4 multiplied by itself adds pi on 4 again, you can see it's on the the purely imaginary axis there, the positive imaginary axis in that case. And the same thing happens for the other solution that you've got, the other square root. This guy here, I'll get rid of that one, minus 1.285 minus 1.285i. What is its principal argument? Well, it's going to be not pi on 4, but negative 3 pi on 4. And when you go from the positive real axis, you go negative 3 pi on 4. If you go another negative 3 pi on 4, that's the same as negative 3 pi on 2, which is the same as pi on 2. So again, you're back on the real axis. Sorry, the purely imaginary axis. I keep on getting that wrong. So this is really delightful to me, right? That in order to get a square root of a purely imaginary number like that, then you're going to have its complex square roots being either here, you know, it's got an argument of pi on 4 here, so pi on 4 again, brings you up to pi on 2, or you could be on the other side and you're going to go minus 3 pi on 4, then minus 3 pi on 4 again, which is minus 3 pi on 2 in total, which is the same as pi on 2 in the principal argument. So let's come back to our graph. That's what happens when A equals 0, and we've already investigated what happens when A is negative. Now let's think about B, right? Here is the hyperbola. It's changing, it's going sort of in and out, it's like breathing. Now what happens when B becomes negative? Watch carefully where the hyperbola goes. it crosses over, just like the other hyperbola, right? Which shouldn't be surprising because these are both hyperbolas, just in a different orientation. When you go to B being negative, you have answers in the opposite quadrants. So, when B is positive, you're getting solutions in the first and third quadrants. When B is negative, you're getting them in the second and fourth quadrants. Which brings us back to something really important that we looked at earlier when we were first looking at square roots and getting them in rectangular form or in exponential form. Doing it in exponential form is really nice and neat because you arrive at this result down here. It's just plus or minus this. One of the things we didn't notice though is, it's quite sneaky, right? Is that in its current form, the two solutions that I have for this particular, this is the particular complex number we were having a look at before to find its square roots. When you have a look at these two solutions, I haven't written them properly in exponential form. What do I mean by that? Well, there's a negative case and a positive case here, right? Plus or minus, that's what it means. So you've got minus 2e to the I pi on 3. And then you've got the positive case, 2e I to the I pi on 3. Now, this complex number over here, this square root, this has no problems. This is already written nicely in exponential form because you've got 2 being the modulus and then pi on 3 being the argument. So this all looks good. It matches what we want. This is in r e to the I theta. But when you have a look over at this is actually not written in the right form, right? Because even though you have an argument over here, it actually doesn't make sense because that's not where this complex number is. It is not found by rotating pi on 3 radians from the positive real axis in the anti-clockwise direction, nor is the modulus negative 2 because the modulus can't be negative. It's a distance after all. So in fact, in order to get what this actual number is, we have to think about where it is and then correct the modulus, make it positive, and then therefore get the appropriate argument. Now, how do we do that? Well, the easiest way to think about it is there is a relationship between a complex number and what happens when you just slap a minus sign on the front, right? If we think about this in rectangular form, you can see how this is all interconnected. If you think about some random complex number and what happens when you slap a minus sign on the front, what's that equal to? It's minus a minus ib. So it's in the opposite quadrant, right? This is what we're looking at on the graph here. You can see here's one solution. This one happens to be in the second quadrant, and here is its opposite in the fourth quadrant, right? So you can see in order to convert that properly, I'm going to have to say, well, if this one here, I know where that is. It's in the first quadrant. So let me just quickly draw it. It's going to look like this. Oops, I'm going to go pi on 3 radians like that, and then that is my modulus of 2. So this is 2e to the I pi on 3, whereas its opposite, well, if I go down in this direction, this would be minus 2e to the I pi on 3. But noting the symmetry here, if this is pi on 3 radians, that means this guy here is pi on 3 radians, which means that coming from the opposite direction, this must be negative 2 pi on 3 radians because they're supplementary angles. What that tells me is that the modulus is still 2, but the correct argument, the principal argument, in this case is actually 2e to the I negative 2 pi on 3, right? So what I'm trying to get across here is I have this relationship which is on opposite sides between my two solutions, and that's what you can see by varying the value of b. You're always going to be on those opposite sides because the two branches of the hyperbola are always in opposite quadrants. The last thing is when you have a look at b equals 0. Let's have a look at that right there. Whoops, my fingers are too stubby. I'll get it. So close. I wonder if I can just type. There we go. That's better. So, b equals 0. I've just forced it there, right? What does this mean? Well, if b equals 0, coming back to our original question, what that means is when you have a look at this arbitrary complex number, there is no imaginary part. A plus I times 0, it's just an a, right? So now what we're thinking of is not the square root of a complex number, we're thinking of the square root of a real number. And not just the principal square root, we're thinking about both square roots. So now if we come back over to our graph, if I pick a value of a that's nice, something like say 9, okay? I've learned, just type it there. So in this case, if I've got a equal to 9 and b is equal to 0, I'm just finding the square roots of 9. Well, you can see there are two of them. One's at 3 and one's at -3. We only take, usually when we're in real number land, we just think about the principal square root, which would be +3, but in complex numbers, -3 is just as valid. So it's not the principal square root, but it is one of the square roots nonetheless. So, what conclusions can we draw? When you're having a think about square roots of a complex number, please think not just algebraically, not just arithmetically, but also visually. There is this wonderful relationship in terms of the arguments and the angles, in terms of the symmetry around these graphs when you wrap your head around these strange hyperbolas and how they interact with each other. And you can also see that a lot of the conclusions that we drew had to connect together. You know, for instance, our understanding of complex numbers in exponential form and our understanding of complex numbers in rectangular form, they all interweave very closely together.